Okay, we might as well start. So first, are there any questions? I think, I know I'm covering a lot of material, and it may not always be interesting to all of you, but you might have some questions. Any kind of a question. When we talk about rho vibrational, we're talking about the infrared. The infrared is one way to measure species. So the species that we might want to measure in combustion, you might say CO2, you might want to measure these in some experiments. Absorption is one way to do that. And those two species do not really have convenient visible or UV spectra. So we go to the infrared. And increasingly, lasers are more and more available in the infrared. So, and increasingly, these lasers are becoming available at longer wavelengths where the absorption bands are stronger. So the infrared is an area where of kind of emerging opportunity for measurements in combustion gases. If you're measuring reactive radicals like diatomic radicals like OH, CH, CN, we would probably measure those in the UV or the visible. Those would be rho vibronic transitions. So we haven't got there yet. So you can kind of think of, if you're interested in species, well, which species absorb? Nitrogen's hard to measure. It doesn't absorb really any place convenient. Hard to measure. So depending on the species, you decide whether you're going to go in the infrared, you're going to go into the UV, and then you have to say, well, where's the best place to make those measurements? What method? Absorption, fluorescence, Raman. But we start with here. We do the rotation, then we add in the vibration, and then later we're going to add in the electronic part. That's when it means we're moving towards the UV. Transitions are stronger in the UV because we're talking about changing electrons. We're changing the dipole moment. So those are going to be stronger absorptions. In the infrared, we're talking about, well, we can only look at modes that have dipole moment, and it's really a question of how much does that dipole moment change with the transition. So usually the IR transitions are quite a bit weaker. But it's really the only way to measure CO2, and water, if you're interested in those species. And of course, they're kind of major species. So we spend a lot of time at Stanford working on trying to make more sensitive measurements of these species in the infrared. And we can measure with some tricks, tens of parts per million in our extractive experiments. So we spent, 4 lectures, introduction, a lot on how do we think about where the bands are and the lines are. Remember, I tell you we have to worry about line positions, line strengths, line shapes. So now we're going to talk about how do we get to strength. This will involve introducing some new concepts for most of you. And then in the last lecture of the morning, we'll talk about line shapes. So at that point, we will have, in 6 lectures, we'll have kind of been through all of these categories of positions, strengths, and shapes. I'm particularly interested in deriving Beer's law. That's the governing equation for the attenuation of monochromatic light that we use as the basis for both absorption and fluorescence measurements. It's a little bit different for Raman that we're not going to be talking about. So I want to derive Beer's law. And to do that means we have to introduce the Einstein theory of radiation. Of course, Princeton is a home for Einstein for a long time, but I think he did this fundamental work when he was probably back in Germany. So we're going to introduce the Einstein Theory, which is the microscopic view of how we talk about radiation strengths. This will introduce the spectral absorption coefficient we need, and there'll be a concept of Rady of Lifetime, and finally we'll talk about line strengths. So what you want to imagine is that we have some sort of a collimated beam of laser light coming in, passing through some sample of gas of length L. And for simplicity, we assume that the composition and temperature are uniform across this length L. So we've got some collimated beam that we can get with the laser, and some attenuation occurs by virtue of absorption, and so the light that comes out is somewhat weaker. And that governing equation is that the transmitted intensity is the incident intensity with an exponential decay law, e to the minus k nu L. L is the length, and k nu is the spectral absorption coefficient, meaning the absorption coefficient at frequency nu. This would be the same equation we would use if it's a CW laser or a pulse of laser light, same equation. Or if we define this intensity to be in watts or watts per unit area, we can define it different ways. But where did this equation come from? And an important point is this only applies for monochromatic light. People use a broad light source. Beer's law doesn't apply. So we want to see where this very important equation comes from. And I introduced this by doing an energy balance. Imagine we have some light going through this incremental sample of length dx. And so the sum of the light which is absorbed or reflected or scattered or transmitted must be 1, conservation. So some of it comes out. And that which didn't come out was lost somehow by scattering, perhaps from particles that might be present, reflection if there's maybe some surfaces of some kind, and some absorption. That's the one we're interested in. Now we define the spectral absorptivity. Absorbance is alpha. That's the fraction of light absorbed. And and this is the fraction transmitted. So in the limit that we imagine a situation without any difficulties of reflection and scattering, these two sum to 1. And we write this absorbance as the product of k nu times dx, because this is a fraction of light that's absorbed over this length dx. And this is the proportionality factor. So this is the absorption coefficient per unit length. And that's the length. Taken together, that's the fraction of the light that's absorbed. That's the fraction that's lost. No units. So this spectral absorption coefficient K is the thing we really wish we understood. How do we calculate this? What is it? It's the fundamental quantity. And how do we find it? In terms of what properties? It's no longer a property of the molecular structure that we've been dealing with. So I want to remind you that these I's can be defined in different ways. It might be power in watts, or watts per unit area, or watts per unit area per unit frequency. It can be defined different ways. It doesn't really change the basic idea. Now, if you were to integrate over the frequencies of some narrow frequencies, then you might get a total intensity I. So I nu is usually reserved in this derivation for the power per unit frequency, or power per unit area per unit frequency, like this. So don't pay too much attention to the units right now, but there's some flags that you have to keep in mind at some point. So we do an energy balance. And we say some light comes in, some light comes out, and there's an incremental change over this incremental length dx. First thing is we recognize there could be some emission taking place. So we introduce the spectral emissivity, which is the emission relative to the black body value of emission at frequency nu. So this is the emissivity at frequency nu. So you have to accept that there is a known relationship for the black body spectral radiancy as a function of temperature, which is well known. It's the Planck distribution. Then there's something called Kirchhoff's law, which says that the emissivity must equal absorptivity. And that's just saying that if you look at an equilibrium case, in equilibrium, all microscopic processes are balanced. Forward equals reverse. So you go to equilibrium and you say, well, this relationship has to hold there, and then some of these relationships hold independent of whether you're in equilibrium. So emissivity equals absorptivity, and that's called Kirchhoff's law. That just says that the emissivity at frequency nu must equal the absorptivity. You can ask some subtle questions about when this breaks down, but we accept this. So if we write the emission as the spectral emissivity times the black body function, which is a known quantity, and this is the absorption, then we can say that this increment di is nothing more than the difference between the emission and the absorption that takes place. So here's the emission term, here's the absorption term, here's the substitution with Kirchhoff's law, and I'm left with a simple relationship here. Now if you remember that alpha is k nu dx, I now have derived on one slide the so-called differential form of the equation of radiative transfer at frequency nu. So remember now, we're not worrying right here about scattered light from particles or reflectivity. Think of it as a pure gas. Okay, that's the governing equation in one slide. So now if we take that governing equation and we integrate over the path length L with the assumption that properties are uniform along that length L, which is not always true, we get the integrated form, which is I nu, which would be that's the emission that's coming out, would be the incident emission, incident intensity, exit intensity is the entrance intensity with the attenuation term and the black body term. All now, there's only one physical variable here, K nu. We haven't found it yet. That's really what we're after. This product, K nu L, is called the optical depth. And if that number is small, we call it optically thin. If that number is large, we call it optically thick. And these equations have certain limiting forms in those limits that are useful. So again, I want to imagine we've got this anticipated shock tube experiment in which we've heated some gas, we're sending in some light, we're measuring the transmitted light, and we're going to interpret that in terms of the concentration of the absorbing species or the temperature, something like that. Now we're going to look at two cases. Let's look at emission and absorption, starting from this equation here. The integrated form of the equation of radiative transfer, done in 2 slides. Looks at an emission experiment. So this is a case where we, oh, okay, I'm violating my Stanford rule again. I have to, oh, we're back, good, okay. I'm out of compliance somehow with some rule. Okay, so let's look at an emission experiment where we have no incoming light. So I nu essentially 0, cold. So now I take my integrated equation, unable to detect. Do I want to continue? I think I want to continue. I hope this doesn't act up too much here. Let's see. I'm going to say, try to cancel this. Does that work? No. I want to continue anyway. Yes. Okay. Hope this doesn't keep happening. All right. So we have this form, and so we can. Oh gosh. Usually, okay. I think I can take this one off. Yes. Yeah. I hope nobody at Stanford is watching. So now we have the single term. And so this is called the spectral radiancy. That is the emission at frequency nu for a path length sample of L. And it's the black body value times 1 minus e to the minus k nu L. That's interesting. Interesting. So we're looking at emission, but in terms of the absorption coefficient, k nu L, absorbance. So the spectral emissivity is defined as the ratio of I nu over the black body value. So it's this number. So everything depends upon k nu. Now that's interesting. Now I'm not able to advance. I did? I am clicking. Maybe if I click on the slide, you say, with my mouse? Let's see. Okay, good. I always get my help on computers from my students, so that's why professors have students. Otherwise, we don't really need you, actually. Okay, so now we might want to integrate over the frequency. And if we integrate over the frequency, we end up with the emissivity, overall emissivity for this path length. And you get this form. So this k nu L keeps carrying along. Now, you will remember probably, if you had a course in radiative heat transfer, that the integral of this is sigma t to the 4th. That's the Stefan-Boltzmann constant. So right away, what we're beginning to see is that the emissivity of the gas depends upon the absorption coefficient, k nu L. If you tell me k nu L, I really know everything. If k nu L is 0, I get no emission. In other words, no absorption, no emission. If it's optically thick, meaning k nu L is large, I recover the black body result. So if you give me a long enough sample of gas, L long enough, even for small k nu, it eventually looks like a black body. So everything's in terms of the spectral absorption coefficient. Now you can have different types of emission. You can have isolated lines that you might have for atoms, you might have bands, you might have continuum, and so on. But anyway, the key point is that if it's optically thick, that means k nu L is large. If it's optically thin, it's k nu is less than 1. device enrollment. I'm out of compliance here. Okay, so now I want to introduce the Einstein coefficients. And so how many people even know what the Einstein coefficients are? Good, so maybe a quarter of you. Okay, good. Because it's kind of a new concept. I do this usually in 2 steps. I use what's called the simplified theory or the Milne theory. But we now imagine 2 quantum states of an atom or molecule that are optically connected. They can be any 2, but we'll just do 2. So we have molecules that might reside in level 1 or might reside in level 2. The energy difference is h nu. And so now, because we're dealing with molecules, we have to now talk about probabilities. So if you're in level 2, and this is an allowed transition, there's a certain probability that you'll go from 2 to 1 per second. It's the transition probability per second of this happening. And you might say, well, why isn't it just an actual number? That's because when you have microscopic systems, they behave by the uncertainty principle and they have probabilities. But you can't be specific about exactly when this is going to happen. But there is a number that represents this probability. And the rate at which that happens in molecules per second would be the number residing in 2 times the probability per second of this process. So that's the total number per second doing this. Meanwhile, if there's emission, there must be absorption, and we can sometimes call this induced absorption. So we say, well, there must be some probability of going from 1 to 2. And in the Einstein world, this is given by the product of the energy density, energy photon density times a number, B12. So the B stands for the Einstein B coefficient, 1 to 2. This is the Einstein coefficient for 2 to 1, because you always have to have microscopic processes balanced. So these A's and B's are the Einstein coefficients for the 2-level system of this atom or molecule. Rho is a little bit confusing. We get away from that pretty quickly, but this was the way it was done in the early days. So B12 is the probability that a molecule in 1 exposed to radiation of spectral density, strange units here, joules per cubic centimeter per hertz, will absorb. So basically, it's how much, depends on the radiative intensity. If you send in a laser of stronger, double the intensity, you're going to double rho, and you're going to double the rate at which this happens. So the Einstein coefficients are these A's and B's, and 2 of these processes depend upon the radiative intensity at that frequency. A does not. So here's now the same thing again. So these are the total rates at which these things happen. So what we do is we do what's called detailed balance. We imagine a situation where we have the net rate of change of the dot is the time derivative. The time derivative for N2 due to these radiative processes only is the rate of population minus the rate of decay, which at equilibrium must be 0. We frequently look at examples at equilibrium, and then you can take certain relationships and apply them away from equilibrium. So let's see. We can solve this equation to get this result. But you also know from yesterday's lecture that this is the ratio of the degeneracies times e to the minus h nu over kt from statistical mechanics. Now we have a temperature here. So this is the radiative equilibrium, this is statistical mechanics. And you also know, not from my lecture, but you could look it up, that the Planck's blackbody distribution for equilibrium radiation is given by this expression here. It's Planck's law. So knowing this, we can then use this relationship here to find this constraint. So that rho must also equal this, as well as this. So rho equals this, which is carried over here, but we're solving for rho over here, we get this result. So these 2 things must be equal. And how can they be equal? They have to be equal at any frequency and any temperature. Therefore, it follows that this quantity here must be 1. That is, whatever G1 B12 must equal G2 B21. So in other words, this is a relationship between the up and the down Einstein coefficients in terms of the degeneracies of the processes that are determined, given to us from statistical mechanics, and the properties of the molecule. We also can solve for A in terms of B. So what we've learned here is we don't yet know what A and B are, but we know how the B's are related and we know how the A is related to the B. So that means that if you give me any one of these coefficients and knowledge of the G's, I know everything. This is the probability per second of emission, spontaneous emission. And that's usually written as 1 over tau, where tau is the average radiative lifetime. So if you put a molecule in level 2 and you watch it in the absence of any collisions, on average, how long it lives there, that's the inverse of the probability per second of emission. So this is the simplified Einstein theory. Now, I don't like rho, confusing units, so we can write it in terms of the number density of photons in a collimated beam times the energy of the photons, h nu. Now, if I want to get this back to the intensity, it's the intensity at frequency nu. So you can find a simple relationship between this Einstein parameter rho and the intensity of my laser. So this would have units of watts per square centimeter per unit frequency. So I can write this now in terms of I instead of rho, which I find confusing. So there's still this big question about what is the shape of a line and do we care? So we don't know yet. We pretend we don't know. So we have Beer's law, and we have this definition for K, and what we're trying to do is find K in terms of an Einstein coefficient and possibly something to do with this line shape. So we postulate that there's a line, that the line has some arbitrary width of delta nu. We don't know what it is, which means that the K must have this shape right here. It's the inverse. It has to be, K can only be finite if there's attenuation. So we say K is of this form, some arbitrary width delta nu, we don't know what it is. So now what we do is we go through energy analysis again, and we talk about the absorbed power. And now the absorbed power will only, see, the absorption is only going to take place in this region. Absorbed power depends upon the intensity in this region times the width. Oh dear. Time to complete. The trouble is I've never been able to figure out how to complete this thing. Okay. I don't know how often it comes. What? Excuse me? You have to put them, okay, okay. Okay, so we do basically conservation energy of balance, and we recover in the optically thin limit, we get this number, fraction absorbed. So we're trying to find K in terms of the Einstein coefficients. And we're worried about the role of the line width. So we're going to find the fraction absorbed using the Einstein coefficients and this line width. So we go back and we do the same kind of analysis we did before. There's induced emission, spontaneous emission, induced absorption. We're going to imagine we have collimated light, so we can throw that term out. We look at the induced emission term. Now, when I use lowercase symbols, that's usually number per unit volume. And if I use a capital N, that usually means total number. So that's the molecules per cubic centimeter, per square centimeter in state 2, times the probability times the energies. So I'm keeping track of the emission term, the absorption term, making use of my simple relationship here, going back and trying to solve this equation now, and I find K. It's just algebra. This allows me to find K, the spectral absorption coefficient per unit length, in terms of a coefficient. I could have written this in terms of A or B21, and does depend upon the line width. And so this tells me that I better pay attention to the line width, so that this K is going to depend both on an Einstein coefficient and something to do with the shape of the line. So at this point, I realize that I cannot neglect the shape of the line. So we now go back and say, let's do it more carefully, and we'll take into account actual line shapes. And this is a juncture between two different lectures, so it's a little bit rough right here. But what I've done is I've shown you the absorbance that you would see if for water, 10% water, path length of 5 centimeters at different pressures. And these are probably spectra we measured in my laboratory. No, it's simulated from high train. And these wave numbers of 6,000 wave numbers means it's around 1.5 microns. So here's the 1 atmosphere case. Here's the 10 atmosphere case, and here's the 20. So what you'll see is that the shape of the line changes with pressure. Okay, and this is a simulated result. So the absorbance, which is related to, which is the KDL, is dependent on conditions, pressure and temperature. So it's kind of motivation for paying more attention to these line shapes. All right, so we go back to this problem here. This is where we were before. We found that this K did depend upon this line shape, 1 over the width. And so, having been through this a few times, I can see this and anticipate that this, when I do the more correct analysis, everything's going to stay the same except this 1 over the width is going to be a height term. And we're going to call it phi for the line shape function phi. So we're going to get the same answer when we are more careful. So we're going to use a realistic line shape function. Instead of using this, we're going to assume that it's something like this. And we're going to have to do the analysis at individual frequencies within that shape. So that K nu is going to look something like this. So instead of being rectangular, it's going to have a shape. And we're going to call that width at half of the peak height. We're going to call that the full width at half maximum. And we're going to define a line shape function so that the integral is 1, so that it looks just like K, but it's normalized so that this area is 1. That's what we're going to do. So we're going to include the line shape. And when we do this, we now are going to go across K, and we're going to, so this, we're going across the transmission, we go across K, and the line shape function mirrors this. So whereas this Beer's law is unchanged, by introducing this line shape function so that the integrated area is 1. Notice if I integrate this over frequency, the integral of phi d nu is 1. So we define line shapes. This is called a normalized line shape function. I do some hand-waving arguments here and tell me that I'm going to anticipate where I had this 1 over delta before, I'm just going to get a phi. That's what we're going to anticipate, but now we're going to go through it. So now we go back to this model, and instead of having this rho term, that rho of nu term, we now have the line shape function d nu. So this taken together is the same meaning. It's the transition probability per second in this frequency range. So now we're doing it in a limited frequency range, specific frequency range. But we still have the A's and the B's. The definitions are shown here. Probability of spontaneous emission in this range. So I have to multiply this together. That would give me the frequency range, and that's the probability. So the integral of this quantity over frequency would be A21, and so on for B's and rhos, using my definition here of how to convert from Einstein's rho to my I nu. So we do energy conservation. We just go through the same thing we did before, energy conservation, and we end up with the answer. K nu, H nu over C, everything is exactly the same except here we have phi instead of 1 over delta nu. So we're done, actually. We now have the absorption coefficient, which is all you need to do either emission or absorption in terms of a line shape function. So this would be for a specific line in the vicinity of that line. So across this frequency range that encompasses this line, this is how this quantity varies. So in order to calculate K, I need to know T, I need to know B, and I need to know the number density of the species in level 1. Most of the time, this term here looks like 1. This H nu over KT is frequently a big number. So it's really, the K is linearly proportional to the number density, the Einstein probability, and the line shape function. Now, we want to get to what I call the line strength. And so we take the integral of this quantity, the integral of K nu d nu. And so if we've used frequency units of hertz, or seconds to the minus 1, and the units of K were per unit centimeter, so the units of this are going to be centimeters minus 1, seconds minus 1. And so that then is what we call the strength of the line. The strength of the line, which is the integrated absorption coefficient, is just dependent upon N and B. If you let this term be approximately 1, it's just the product of N and B. If you increase the Einstein probability or you increase the number density in level 1, you get a stronger strength. So the strength is really the integral of the absorption coefficient. If B is 0, the number density is 0, there's no absorption, there's no emission. So the strength does not depend upon the shape. The spectral absorption coefficient depends upon the shape, but not the strength. Now there's lots of units that roll around in this area of spectroscopy. Right now, so you have to keep track of the units. In this case, they're centimeters minus 1, seconds minus 1. There's also different approaches. You could have written this in terms of B, or A, or F. F is a historical thing. It's called the oscillator strength. There's different ways of saying the same thing. We care about is S. And so if you have access to a tabulation in terms of the oscillator strength or A, either one will work. The units of this are a little crazy, so you have to be careful. Electrostatic units. That's called the oscillator strength. And we use that more when we deal with rho vibronic spectra. We don't really deal with it in the infrared. And it has a meaning. And it's set up so that F is a number that kind of ranges from like 0 to 1. And it's a probability, fractional success probability. The actual line strength divided by what's called the classical value. And that's because some theoretician did the strength of a line for a transition that involved a single electron dipole and got a number. And so that's called the classical number, and that's this thing right here. It has particular strange units. So somebody did the analysis for a freely moving electron and found that this is the probability of a line strength for that case. So F is a number, and if you say if this number is big, like say 0.7, that means it's a very strong transition. If it's 10 to the minus 3, oh dear, if it's 10 to the minus 3, as we'll find it is for an electronic transition of OH, then that means it has it's not so likely. Usually what we find is in the infrared, because these do not have strong dipoles, they have very small values of the oscillator strength. Okay, so this is just summarizing this. I got the same problem, huh? I think this problem will dissipate if I took the time to get rid of turn it off and start again, but I won't do it now. We always have to make use of this relationship that P equals NKT. Remember now we're talking about the number density in a state. That's not the total number density of the species. So just to remind you how big these, oops, okay, did I go forward? Okay, I think I'm okay. So we always want to remember, we need the line strength, we need the line shape. So this is the problem. I showed you how important K nu is. Emission, absorption, I just need K nu. But K nu has got to be written in terms of a strength and a shape. And S is the things related to the Einstein coefficients and number densities. So oftentimes this H nu over K2 is much greater than 1. It is for transitions in the UV. And so you can find some simplifying relationships to help us understand the strengths in terms of just an Einstein A coefficient. So you can get some simplifying relations if you leave off the 1 minus e to the minus H nu over K2. So if you tell me A and the degeneracies and the number density, I know S, or vice versa. Typically, we know A, we know G2 over G1, we know S, and we are solving for N1. Typically, the goal is to find N1. There are some simplifying approximations here to relate F and A, just to give you a better feel for this. So this F over A, which is the same as F tau, is 1.5 times this degeneracy ratio, which is just a number, times lambda in centimeters squared. So I'm doing all this because sometimes people will give you a tau, sometimes they'll give you an A, sometimes they'll give you an F. You just have to be able to go back and forth amongst these different systems. I'm going to give you an example of a resonance transition. Resonance transition is one that links the ground state of an atom to the first excited state. That's going to be a strong electronic transition. So if you took a sodium atom, which is in the first column of the periodic table, and you looked at a transition which has this symbolism, which we'll learn about later, that would be this resonance transition. It turns out that the degeneracy ratio is about 1, the wavelength is 590 nanometers, and, or this in centimeters. And so the convention for atoms is that you write the lower state on the left and the upper state on the right. The convention for molecules is the opposite. Why this happened, who knows? Oftentimes you'll see an arrow which tells you whether you're talking about an absorption process, would be from right to left, or emission process. Sometimes you'll see an Fij, and usually the I denotes the initial state and J is the final state. So if we're talking about F12 versus F21. So from this relationship now, I know already how to get F tau. And it's 10 to the minus 9. So just from this simple relationship on the last slide. Now the measured decay time is this, and that tells me A. So where did people get the A coefficients? Where do people get the B coefficients? Frequently from experiments. Exactly how you do those experiments is a different subject. If I measure the absorption in a given line, and I know how many molecules are present, I can find the line strength, and I can solve for B. Or in emission, I might look at the lifetime of a molecule or atom in a state and watch it decay, and I can get that characteristic time, tau, and I can solve for A. So they usually come from experiments. There's theory, but usually the ultimate test is the experiment. So the Einstein parameters, which have a fundamental meaning, still require, and are depending on the atoms and the molecules, are usually experimentally determined. So if we do this particular case of a resonance transition, I get an oscillator strength of 0.3. So what I told you was, it's often a very, very small number, because it's normalized by this highly probable free electron case. This is strong. 0.3 is still a big number. Maybe I can get rid of this. So here's just an example values. These are all sodium. So sodium is, because it's got just one unbound electron, that means it's the closest you're going to get to the freely moving electron case that was the classical limit that someone solved for. These are different transitions that you don't need to understand right now. They're different transitions, but you can see they have different values for F. If you know about the sodium spectrum, you know that there's a doublet, there's two lines near this wavelength, so that there's two values and they sum to nearly 1. But if we go to molecules, let's look at a molecule, CO, and we're going to do 0 to 1. So what's that called? It's vibrational transition. It's the fundamental. Not electronic. It's band center, 2143 wave numbers. That's 4 microns, 4.6 microns. The oscillator strength is 10 to the minus 5. So if you looked at that number, you'd say, wow, that's pretty small. Yes, it's very small. So the infrared absorption strength is a lot less than the corresponding electronic strength for sodium. If I go to OH, however, now this is pure vibrational. That's the fundamental of OH, 10 to the minus 6. If I go to an electronic transition of OH, 10 to the minus 3. So the oscillator strength is a number that really characterizes, in kind of 0 to 1, the strength of the absorption or the emission. And this is electronic transition, electronic transition. This is the biggest one that I know about. For a diatomic radical, the absorption strength for CN is really big. Oscillator strength of 2%. So the F oscillator strength, which is used more in the UV for people, is a simple way to characterize the relative strength compared to the theoretical limit of the classical limit. When you're dealing with rho vibrational, the numbers are smaller, but that doesn't mean it's not useful. It just means that it's small on that scale. Okay, Rady of Lifetime. If you have a molecule or an atom in an upper state, and it can decay by radiative processes, that would be the spontaneous emission. There's no collisions here now. I can write a differential equation for the rate of change of the population or rate of decay. So I put some atoms up here and I watch how fast they decay. The rate of decay would be given by the differential equation, but I have to sum over all the possible radiative paths, all of the AULs. So if I have an initial population here, there will be an exponential decay. That's the thing to know. This different form of differential equation always leads to exponential process. So the number density and the time resolved number density is the initial value with an exponential decay. And that average rate of lifetime, which means in the limit of no collisions, is 1 over the summation of the A's. In the real case, there's the molecules up here, and there are going to be some collisions. And so we'll treat those by calling that the non-radiative decay. It's the same differential equation, where now K is a rate coefficient for removing that atom or molecule to the lower state. We get the same exponential form, but one depends upon, this is the number of density in the upper state, one depends upon the rate coefficient, which will be linearly proportional to the number density of colliders. So one depends upon pressure and one does not. And if you recognize that in general they're both there together, I wonder if I can take that off further, you can rewrite the rate equation as the sum of the two terms. I'll put this back up here. As the sum of the two terms. And so that would be the observed lifetime. So the observed lifetime depends upon radiative and non-radiative processes. Imagine there's, in the zero pressure limit, you see only the radiation. In the high pressure limit, you see the collision term. So there are different expressions for lifetime. Radiative lifetime, non-radiative lifetime, observed lifetime. You have to be careful about those words. Okay, now I'm just going to zip through this. There are a lot of different units that are used for the property we care about, K. It's per unit length. K is always per unit length. But it can be obtained always by the product of S and phi, but these terms may have different units. S might be in centimeters to the minus 2, and phi might be in, the units of phi are always, oh my word, the units of phi are always inverse with whether you're using frequency units of seconds or wave numbers. I think if I turn this off later, I can maybe minimize this a bit. I'll do this again. So I'm just going to alert you that you really got to pay attention to the units. They keep changing. And so S is always related to the number, is always proportional to the number of absorbers in that state, N1. How do we get N1? We apply Boltzmann statistics to the total number density of that species. In the infrared, we tend to use units that look strange to you, centimeters to the minus 2 per atmosphere. Why, I don't know. But that's the way it's done in the infrared. Frequently, you'll get units of centimeters to minus 2 per atmosphere, or if you go to high tran, you might see these units. You have to be careful. And you have to be very careful because the temperature dependence that's implied in these different expressions is off by 1 over T because P equals NKT. So you have to be careful about the units, especially when you try to scale. So high tran will use units that look something like this. They'll have their line strengths in these units. But a lot of times in literature and in Stanford literature, we'll use these units. So they're always related through P equals NKT. So this is the relationship between the units we use at Stanford typically and the high tran units. There's always a conversion factor between dynes per square centimeter in atmospheres and a KT running around. So you can work it out, but you just have to be cognizant that the units may be different in different papers. A lot of different forms. Beer's law is always e to the minus KL. When you deal with a small molecule, discrete spectra, we typically will use K, and then we might replace that with an SVPL, because K is the product of a line strength and a line shape and a partial pressure. So if I have centimeters minus 2 per atmosphere and centimeters minus 1 units, this is centimeters, atmospheres here, centimeters here, centimeters here, I end up with the bright units. So that's the units that we often use at Stanford, but you'll see different forms. If the molecule is larger and we don't want to resolve the spectra, we typically will use a cross-section. So it's still proportional to the number density of the absorber. So here's the total number density of the absorber, here's the partial pressure of the absorber, always is the length, always is an exponential decay, but you just have to be careful about the different units that people use. When people say cross-section, they're thinking about this form. So there's no line shape in this. And this means that the spectra are kind of broad and you cast it in terms of a cross-section. All right, so there's just some stuff here that you can refer to if you want to study it in more depth. Okay, temperature dependence is important. Why? Because typically someone will cite the temperature of the line strength at a reference temperature T0. And you have to get the line strength at the temperature of interest. And this is where it depends upon the units. If you're using these units, then, and this is the arbitrary expression for this in terms of any reference temperature, you get this T0 over T. If you do it in the Hytran units, you get the same reference value, same ratio of the partition functions, everything's the same, but there's this missing T0 over T. So that's really what it boils down to. Typically, you want to know the line strength at temperature T. And it's sufficient if you know the line strength at any temperature T0 to convert. All you're seeing are the ratios of the Boltzmann fractions. That's why the partition functions are here. So that's the key. You have to be careful. This tells me that this is just reminding me to keep track of the temperature change. Okay. Sometimes people talk about band strength. It's not so common anymore. Sometimes people will talk about the strength in a row vibrational band instead of the strength of a line. And formally, the definition of that band strength is the sum over the line strengths. And let's see. I go through a procedure here which convinces me that, or you if you were to study it, that if you sum up the line strengths in a certain way, I'm just going to draw a few conclusions from this. See what's next. Okay. If you were to do this for a row vibrational band and recognize that there is, like carbon monoxide, you have a P branch, you have an R branch. You can write the expression for the lines in the R branch. So the band strength would be the sum of the P branch transitions and the R branch transitions. And right now I'm doing the 0 to 1, that's the fundamental. And I'm going from J prime, double prime to J prime. So I can sum over all the lines in this band. Now if I just do the ones in the R branch, this is the arbitrary expression for any specific J. I bring in the degeneracies, the A coefficient. You can convince yourself when you're done that you end up with, because the sum of the Boltzmann fractions is 1, you end up with a simple relationship here. That gives you the link between the A coefficient for the band and the band strength. So sometimes in the old literature, people will talk about the A coefficient for the band or the band strength. Once you have this, you can go back to the line strengths. More likely, you're going to use Hytran, if it's there. But if it's a molecule that's not in Hytran, it's the sort of thing you have to do. Why do I keep showing the A coefficient? The A coefficient has this nice property that is based on just the lifetime of decay. So if you do an experiment which you put some molecules up, pump some molecules into this upper state, watch by emission of light the decay rate. You can measure A. If you measure this at different pressures, you can extrapolate to 0 pressure. There's a name for that plot. And so a measurement of the decay rate is sufficient to get A. Once you have A, you have B, the B's. Alternatively, you can measure the absolute absorption by scanning a laser across an absorption line and measure the B coefficients. But especially in experiments where you can't readily generate known amounts of a radical species, the decay rate measurement is the way to go. And that's where the basis of, say, the oscillator strengths or line strengths for OH, NH, NH2, radicals that are not stable. It's hard to produce known amounts. So rather than use known amounts to get the B coefficients, you just measure the decay rate. This is just an example to show the relationship between the A coefficient and the band strength. So one of my students back around 1980 measured the band strength of CO, and from this we got the A coefficient. What is the A coefficient? 36. What does that say? It says that the average lifetime for vibrational transition is 28 milliseconds. So if you put a molecule of CO in an excited state and you leave it alone, it takes 28 milliseconds to decay. If I put an OH molecule in an excited state for an electronic transition, it decays in a microsecond. So the decay rate, the oscillator strength, the A coefficient, they're all telling you the same thing. So infrared transitions have small oscillator strengths, small A coefficients, probabilities, and therefore weaker absorption. But fortunately, we usually have a lot of CO, or we have a lot of CO2, and we can live with this. Okay, looks like I'm pretty much on time. Maybe I'm even a couple minutes early. So how about some questions? So this is, in one lecture, we introduced the Einstein Theory, and we showed you the importance of the spectral absorption coefficient for any problem in radiative transfer. And we showed you that you do have to pay attention to the line shape. So it's line positions, line strengths, line shapes. What am I going to do next? I think I'm going to, in one lecture, give you line shapes. Then we'll have all the elements that we really need to think about real problems. Okay, and we'll talk about primary types of broadening, Doppler broadening, natural broadening, collisional broadening, and how we put those together in what's called the void profile. Somebody asked me a question about collision narrowing. If you put in collision narrowing, this becomes a Galadriel profile. Okay, see you in 15.